Okay, let's do a titration. So here is a general setup that you would have. Now, a titration is to determine, the purpose of a titration is to determine the concentration of an unknown acid or base. So here is my acid. This is actually going to be vinegar. I'm just going to simulate what we would normally do a titration with. So this would be vinegar, and it's 15 milliliters. I'll add a little bit of water just to increase the volume. That is not going to change how acidic it is, though. It's not going to change the number of moles of vinegar that's in there. Will change the volume, but not the number of moles, and that's what I care about. And what I have in here is sodium hydroxide. So vinegar is an acid. I can prove that to you by taking a litmus paper strip and stick that right there, and you can see it turns it red. So that has a pH, a low pH, which means an acid has a low pH. And then this guy, what is in here, let me go ahead and try to get, there you go. You can see it turns the litmus paper blue. Okay? So litmus paper, blue litmus paper has a very high pH. So we have an acid and a base. So that's what a titration is. I know the concentration of this. This is called my titrant. A titrant has a known concentration, and we were going to measure the volume. That's why we use a burette as a very precise volume. All I know is the volume here. I do not know the concentration. So now what I'm going to do is, as I add the acid and the base together, they are going to neutralize each other. And so they will eventually make salt in water. But I won't be able to see the neutralization because they're two clear liquids. It will just make another clear liquid. But if I add an indicator, this is called phenolphthalein. Now, phenolphthalein does not change the pH of the solution, but it will change colors when the pH changes. Okay, it itself did not change the pH of it, but you'll see. So right now, note the color. It actually has no color, colorless. Okay, so I am going to start. I'm going to note a volume here. Let's say it is 2.45. Okay, hey, always good practice to write that down. 2.45. And then I am just going to add some. So we're getting close to it, and as you can tell, it is starting to be a pink color. So let me add some more. And these, you have to be careful with these things because you'll creep up to it, and all of a sudden you'll hit that point, and it will instantly change colors all at once, and you won't be able to change it back. So you have to be careful. You want to creep up gently. This is very light pink. And there we go. So we are right at that point where it's very light pink. That is right where we want to be. So that would be the end point, the point at which it changes color. Let me show you what it looks like when you push it past the end point. So you can tell that I didn't add too much more, and it became really pink. So this is where it is all basic. So let's, yeah, at the beginning you saw that it was red. So if I took some pH paper now and tested the pH of it, after I've added all that base, I have now gone into the basic spectrum. Right? So I have crossed the threshold from being an acid in here, and I have made it a base. So at that point, when it flips, when it changes from an acid to a base, that's a very important point. That's called the stoichiometric point, or the equivalence point. And that is where the moles of the acid equals the moles of the base. Very, very important. So that was probably, let's say, I added too much, so it's probably around 21. We'll say 21. We'll keep our zeros. So that means that, so I added about 18.55 milliliters there. The volume from here to here, that is the volume that I added. So I have now a known concentration of this, the known volume, a known volume here. Now I can calculate the concentration of that. So the easiest way to calculate that is using the equation of moles of acid, volume of acid equals the moles of base, volume of base. That's because molarity times volume is the moles. Molarity times volume is the moles. So remember I said that was where the moles of acid equals the moles of base. Well, this is the molarity times the volume, or the concentration times the volume. Concentration times the volume. So we can find the concentration of our acid. 15. We had 15 milliliters at the beginning, and then we had the concentration of our sodium hydroxide was 1, and then the concentration and the volume of that was 18.55. Okay, so 18.55 divided by 15 should give you a molarity of 1.23. Okay, that is actually pretty far off from what it's supposed to be. That's because I did it very quickly and did not do very accurate calculations. So let's try to do some more accurate ones, and let's try to do a different type of titration. It's the same kind of deal, except now we're going to do something that's a count by drops. So this is what you do in class, where you're going to use a well plate. Well plate looks just like this. I just rinsed it out. It's all nice and clean. And what you're going to do is you're going to take some vinegar, and you're going to put it, and you're going to note that on that vinegar, the brand of it is the Hill Country Fair, and it is 5% acidity. Okay, that's important for your paper. And then here, I'm going to pour it into a beaker. And instead of using a burette and all that stuff and trying to fight over those and get it all just right, we're going to use something very simple that's very easy, repeatable, and it also uses the least amount of materials. So what I'm going to do is I'm going to take 15 drops here. Instead of 15 milliliters before, I'm going to use 15 drops. And I'm going to have to run 5 trials, so I'm going to do 15, 15, 15, 15, 15. Alright? So I have just added 15 drops of my acid. I'll go ahead and prove to you again that it is red, so that is my acid, my vinegar. And now I'm going to add my indicator, my phenolphthalein. Okay? And I'm just going to add 1 drop to each well plate. 1. Alright. We'll shake that up just a little bit to get it stirred up. And now I'm going to start adding sodium hydroxide and counting the number of drops. Now remember, I put 15 drops of acid in there. I want to count how many drops it takes to neutralize 15 drops. Okay? So, just a little hint. It took us 15 milliliters of acid, and it took us 18 milliliters of base to neutralize 15 milliliters of acid. So I'm going to guess it's going to take about 18 drops to neutralize 15 milliliters of acid, or 15 drops of acid. So as predicted, it took 19 drops that time. About 18, it started to get a little fuzzy. So I'll speed up the rest of it, but check it out and see how it goes. So these are the number of drops that you should have counted, or that you should write down for each of the trials: 19, 18, 19, 18, and 20. That is some pretty good precision, Mr. Russell. So here's the data we have available to us. We have 19, 18, 19, 18, and 20. Okay, so we are going to apply the formula: molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. Okay, so the molarity of the acid is what we want to know. The volume of the acid is 15 drops. The molarity of the base is going to be 1.0. That came off the label because I knew the concentration of my base. And then the volume of the base is going to be 19 drops, because we added 19 drops. Now this guy is always going to be the same for every calculation, but you're going to have to do 5 of these and change that number. Okay, so 19 divided by 15, you can do that on your own and figure out the molarity of your acid. In this case, is going to be 1.27 molar. Now that's a little high. It should be about 0.8, but that's all right. Just a fair warning, because it's going to show up in a second. So eventually you'll do all of those and you'll find the average. You know how to find averages. You should be able to do that. Take all of those, add them all together, divide by 5, you got it. So then you have to find the error. So the way to find the error is to take we're going to use the halfway method. We're going to take the highest one and the lowest one. Well, there's 2 lowest ones. And we're going to take the highest and subtract it from the lowest. And then we're going to divide by 2. Okay? That's the halfway method. So 20 minus 18 conveniently is 2. 2 divided by 2 is going to be 1. Okay? So your error, or your uncertainty, means plus or minus 1. So we are, for each one of these, we are sure that we're sure that it's 18, but it could be 19, or it could be 17. We're not quite sure. This 19, it could be 20, or it could be 18. So that's what that plus or minus 1 means. Okay? So now the next step is a series of steps to be able to get you to determine the percent of vinegar. So the first thing we'll need is the molar mass. That's our CH3COOH. You should be able to find the molar mass of that. Go to the periodic table to find the grams per mole. Okay? Then you are asked to find the grams of acetic acid in 1 liter of vinegar. Okay? So we know our molarity of the acid, right? And we know that the units for molarity are moles over liters, right? Well, what if we just change moles into grams? Okay, how do we do that, Mr. Russell? Well, I bet we could cancel out moles and change it to grams, right? Look, grams per mole, that's your molar mass. Fantastic. So, I won't tell you the molar mass, but you can figure that out. And so you're taking your molarity, multiplying by the molar mass, and that will give you the grams per liter, per 1 liter, whatever that number is. Okay? So now, the last step is to find the percent of vinegar. So what you're doing is every time you find a percent, you're finding the part over the whole. Okay, so you have to think, what is the part, what is the whole? Well, in this case, the part is your grams of vinegar, and the whole is the grams of the solution. Okay, because the vinegar is actually mostly water and partly acetic acid, right? We read on the label that it's 5% vinegar, so it's 5% acetic acid and 95% water. So let's make an assumption here, and we know that the density of water is 1 gram per milliliter, right? So we know that we're going to assume that it's all water, right? So we're going to assume that the whole thing is that 1 milliliter has a mass of 1 gram. 1 milliliter has a mass of 1 gram. That's what we're assuming. So if we said we had 75 grams per liter, okay, then let's change that. Grams per 1 liter. Let's go ahead and change liters to milliliters. There are 1,000 milliliters in a liter. So 75 divided by 1,000 is going to be 0.075. Okay? That's how many grams per milliliter there are. Correct. So that's how many grams of vinegar there are in per milliliter of solution. Correct? So that's your grams of vinegar divided by grams of solution. That's what that is. Now, remember a percentage. You always 0.075 grams per liter. We always have to multiply by 100, right? To make it a percentage, right? So that makes it 7.5%. Ta-da. Okay? So compare that to the bottle. The bottle said it was 5%. So we are a little high. Like I said before, when we calculated molarity, we were a little high when we did this. That's okay. We would have to run multiple trials. Double check this, this base. We should probably standardize this to make sure it really is 1 molar. And I bet you that would clear a lot of things up. All right? So question number 4 asks you to explain why the procedure described in this activity could not be used to analyze red wine vinegar, and then how could the procedure be modified to analyze this type of vinegar. So I'll leave that up to you, and I hope you have a great day.